Welcome to this explainer. Today, we're opening up the dossier on a true marvel of modern stealth naval engineering. This is a system that is quite frankly quietly shifting the entire global balance of power on our oceans. Consider this your Q-branch deep dive into the LRSTD, or Long-Range Surveillance and Targeting Drone. Now, to be clear right out of the gate, this isn't your standard off-the-shelf commercial quadcopter. No, this is a ground-up, highly classified style architectural triumph. And it was built to solve literally one of the most stubborn tactical nightmares in modern maritime warfare.
You see, modern navies face this massive, terrifying vulnerability, the horizon itself. Ships absolutely need to sense and strike targets hundreds of miles away, but sending out a manned helicopter or exposing a massive multi-billion-dollar aircraft carrier to enemy radar just to peek at a hostile fleet? That's an incredibly high-risk gamble. It's essentially putting a giant bullseye on your back. The LRSTD is explicitly designed to close that vulnerability entirely. It allows ships to see, track, and strike targets way beyond the horizon without ever putting a single human crew member in harm's way.
Okay, let's dive into this. Our mission flight plan for today has 5 key waypoints. We'll hit the naval surveillance gap, how they solve the incredibly tricky weight trilemma, the magic behind its hybrid flight and stealth, the AI eyes on the ocean, and we'll wrap up with the unbreakable kill chain.
Section 1. The Naval Surveillance Gap.
To really appreciate this machine, we first have to understand the incredibly high-stakes environment of denied access zones. These are patches of ocean heavily guarded by enemy radar and surface-to-air missiles. Right now, fleet commanders are forced to make a pretty terrible choice. You either push your ship and its thousands of crew members right into dangerous waters to see what's out there, or you just operate completely blind. The source documents identify this specific missing link in current naval architecture: a desperate need for a stealthy, autonomous platform under 150 kilograms that can take off vertically and provide persistent intelligence, surveillance, and reconnaissance.
Moving to Section 2. Solving the weight trilemma.
Building that missing link meant solving what looks like an impossible engineering puzzle. In the aerospace world, you're constantly fighting a battle between weight, range, and endurance. It's like a giant game of tug-of-war. Want more range? You need more fuel. More fuel means more weight. Want it smaller? You give up how long it can stay in the air. So constraint number 1 for this drone, range. It needs to hit a massive 700 nautical miles of operational range. That sends it way past the horizon, deep, deep into enemy territory.
Constraint number 2, endurance. Because it can't just sprint out there and immediately come back. It needs to loiter. The system requires over 10 hours of persistent surveillance capability. It has to just hang out up there, tracking moving fleets and quietly waiting for that absolute perfect strike window. And now we drop the hammer with the final constraint, the absolute nightmare for the engineering team. A strict, non-negotiable all-up weight limit of exactly 150 kilograms. The source calls this the most fundamental constraint of the entire program. Think about this. Just the fuel, the heavy batteries, and the camera payload alone weigh about 90 kilograms. So you're left with barely any room on the scale for the actual airframe, the engines, and the onboard computers.
So, how on earth did they pull it off? Well, they used a brilliant piece of proprietary mass management called a CG-locked architecture. Normally, as a drone burns through 35 kilograms of fuel during a mission, its weight balance shifts drastically. Usually, you need heavy active ballast systems just to keep the thing from literally tumbling out of the sky. But instead, the LRSTD packs the heavy fuel tank and the battery right at the absolute center of gravity. As the fuel burns off, the physical balance of the aircraft remains locked within a tiny 2% margin. It's such an elegant, weight-saving solution. And this brilliantly illustrates how the whole thing comes together. To stick to that strict mass budget, the engineers had to be utterly ruthless. They used an aggressive carbon fiber composite structure, targeting a mere 40 kilograms for the airframe itself, and combined it with modular payload bays. That's how they kept the drone strictly under budget without giving up an ounce of capability.
Section 3. Hybrid flight and stealth.
To actually get this thing moving through the air, they had to mash up 2 fundamentally different modes of flight into one single airframe. Taking off from a super-crowded naval destroyer deck means you need vertical takeoff and landing, or VTOL. So for the ascent, the LRSD spins up 4 to 6 electric quadcopter rotors for a smooth, near-silent hover. But here's the catch. Electric rotors cannot push an aircraft 700 miles. So once it's up in the air, a rear-mounted internal combustion engine running on standard naval JP5 heavy fuel kicks in. This pushes the fixed-wing airframe forward into a highly efficient long-range cruise mode.
But merging these two modes introduces a terrifying risk. The source actually notes that the transition phase, the moment you transfer lift from those vertical rotors over to the fixed wings, is where 80% of all hybrid designs fail. It creates this dangerous instability zone. To survive that handoff, the LRSTD relies on a proprietary blended control law. It does the math in real time, smoothly ramping down the rotor thrust in exact inverse proportion to the lift that's building up under the wings as the drone speeds up. It keeps the flight perfectly, flawlessly stable.
So, once it's flying smoothly, its next job is to disappear. The drone manages what's called a multispectral stealth matrix. Basically, it hides across the board. To beat radar, it uses a blended carbon fiber fuselage coated in radar-absorbing material. To beat thermal cameras, it uses a clever S-shaped exhaust duct with ceramic cooling, which completely masks the engine's heat signature. And to beat acoustic sensors, it runs a custom, low-RPM scimitar propeller. For all intents and purposes, this thing is practically a ghost.
Section 4. AI Eyes on the Ocean.
But hey, a stealthy ghost is pretty useless if it's blind, right? Running entirely on the edge, using an NVIDIA compute module, the drone's digital brain is built for autonomous targeting. To pull this off, it runs a YOLO V8 and deep sort hybrid neural network. Now, to put that into plain English, this AI engine is simultaneously gobbling up high-resolution 4K visual video and thermal infrared data. It fuses those streams together to continuously detect and lock onto targets. So even if an enemy ship tries to hide in fixed sea fog or the pitch black of night, the AI still sees it.
The AI's actual thought process breaks down into 3 distinct cognitive layers. Layer 1 is perception. That's spotting basic shapes like ships, submarine periscopes, or even just the wake pattern a ship leaves behind. Layer 2 is tracking. This is maintaining a persistent, unbreakable lock on 10 or more moving targets all at the exact same time. And Layer 3 is decision, where the AI classifies the threat by vessel type, speed, and heading, and then instantly generates a precise targeting packet.
Now that sounds great in theory, but out in the real world, the open ocean is notoriously tricky. The engineers had to beat something called sea clutter. That's when crashing ocean waves, a weird glint of sunlight, or just floating debris trick standard AI into thinking it sees a battleship. The LRSSD solves this massive headache using something called 5-frame temporal validation. Essentially, the AI forces itself to confirm the target across 5 consecutive streams of video before it alerts the fleet. It virtually eliminates those annoying false positives.
Finally, Section 5. The Unbreakable Kill Chain. Okay, so picture this. The drone is launched, survived the dangerous transition zone, remained totally hidden, and its AI has locked onto an enemy target. Now, it has to talk back to the fleet to complete the kill chain. So the crucial point is, this communication data link has to be ironclad. It cannot be intercepted or jammed. The drone uses an encrypted ISR GSAT military band satellite connection. It's packing AES-256 encryption, adaptive beamforming, and frequency hopping specifically to survive heavy electronic warfare. And if the enemy somehow still manages to jam the signal, the drone just shrugs it off, entering an autonomous fallback mode where it navigates strictly via internal sensors without needing any outside links at all.
But make no mistake, this entire system is balanced on an absolute knife's edge of extreme engineering. The source's critical risk register points out a massive danger we haven't even touched on yet: battery thermal runaway. When you push high-powered AI computers and high-voltage VTOL batteries to their extreme limits inside a tightly sealed composite fuselage, you generate immense heat. And a catastrophic battery fire on a crowded naval deck, that is a nightmare scenario with incredibly high human stakes. To prevent that, the drone uses dedicated liquid cooling loops and thermal isolation chambers to keep the beast properly chilled.
Let's move to and see how this builds into the ultimate tactical advantage. The LRSTD is out there, hundreds of miles beyond the horizon. It detects a threat. It neatly packages the precise latitude, longitude, and velocity of that target into a tiny, heavily encrypted data packet. It then relays that packet via satellite directly to the host ship's combat management system. And here's the magic. The host ship can then launch its own long-range strike vectors, destroying a target 700 miles away without ever having to turn on its own revealing radar.
This brings us to a really defining statement. Let me read you this quote directly from the technical annexer itself. The LRST transforms every Indian Navy warship into a distributed, long-range, AI-powered sensor shooter node. That hits the nail right on the head. This isn't just a fancy flying camera. It is an absolute strategic transformation of naval domain awareness.
We've really just explored the bleeding edge today. from stealth composite design and complex thermal management to multimodal edge AI. But all of this leaves us with a truly fascinating final thought to ponder. As autonomous AI and hybrid aerospace engineering continue to merge flawlessly into incredible platforms like this, how will the LRSTD fundamentally reshape the future rules of naval domain awareness? It certainly seems like the horizon is no longer the limit. Thank you so much for joining me on this explainer, and I'll catch you next time.